So today we have PJ talking to you, and I'm excited about PJ. PJ has worked on one of what I consider to be JPL's most successful projects ever. And it's one of the things that actually intrigued me about coming to work at JPL. So PJ has worked on a couple of very exciting projects, Galileo and as currently the Insight, and I will let him take it over from here. Thank you, PJ. It's all you.
So, you're doing what on Mars? So, good morning. At least I think it's morning where you guys are. I get confused, and let me tell you why I'm confused. This morning I was working on a plan for activities to take place on the Insight project, and we were talking about 3 different time references. The plan that we're working on starts this coming Saturday, which happens to be the 28th of September, but it also happens to be the 270th day of 2020, and then we call it Sol 652 because the Insight lander has been on the surface of Mars for 652 days, or it will be at that point. And of course, a Martian day isn't the same as an Earth day, which you know is 24 hours. Oh no, a Martian day is 39 minutes and 35 seconds longer than an Earth day. So just let's keep it simple. Let me say good morning. Thank you for having me. I am thrilled to be here. I'm hoping that you will be able to enjoy your time with me. My name is PJ Guske. Here's a picture of me. Lots of gray hair on that face. I am talking to you from a town called Whittier, California. So right there on that circle, that's where I am. And to put it in reference, we are about 15 miles east of downtown Los Angeles, or something that may be more interesting, about 10 miles northwest of Disneyland, which unfortunately is closed right now. So it's 4 o'clock in the afternoon. The sun is shining. I'm looking out my window. It's a beautiful day. The smoke has cleared away, but our air is still unhealthy. So I have some kids who are cooped up inside. You might hear them screaming in the background. Just to prove it to you, this is my family last year at my son's wedding. And we originally had 3 kids of our own, our 3 bigs as we call them, my son and 2 daughters. And then when my son was in high school, we had the opportunity to foster through LA County 3 other children, and ultimately we adopted them. And quite frankly, our lives have never been quiet since. So I grew up in Northern California, and I was the youngest of 3 sons for a high school teacher and a homemaker. So I have a real good appreciation of what your teachers are doing and the hard work that they do. In addition to that, my wife and I have homeschooled all of our children. So I have some idea of what's going on if you happen to be distance learning during these times of pandemic. My hope is that as we're talking today, you'll learn something that's exciting, something new, or maybe it'll spark your continuing interest in something related to science and engineering, especially, in my personal opinion, space exploration, because quite frankly, I think I do some of the coolest stuff, and I work with some of the most impressive people in the world, and they pay me to do it. So I have always wanted to be an engineer. I've always enjoyed math and science. I grew up wanting to figure out a way to combine my love of airplanes and space exploration, and going into the aerospace industry just made sense. I was real fortunate that when I graduated from college, I was able to go live in another country for a year and get my master's degree. The year I spent in England was probably the best thing that ever happened to me, because it taught me a whole lot more than just facts and figures. I learned something real important that I've carried through for the rest of my life. I learned that just because somebody does something different or in a different way than I do, doesn't mean that their way is wrong. It's just different. And sometimes, well, many times, their way was better than mine. So working with people from various backgrounds allowed us at that school there in England to create projects that we could draw on the experiences and the strengths of other people and ultimately build a better project. We were a team that needed to work together, and if one person failed, we all failed. And if we pulled together, we would all succeed together. That was a huge life lesson when I moved to Southern California and I went to work here at JPL, or the Jet Propulsion Laboratory in Pasadena, California. For those of you that don't know, this is where most of NASA's robotic spacecraft are operated. And as Michael mentioned, I was able to work, my first project was on the Galileo spacecraft. This is a spacecraft that flew out to Jupiter to gather all sorts of science. And I don't know if you can tell on this picture, I'm not sure how well it's coming through, but our big high gain antenna was supposed to look like an open umbrella. And something stuck and it didn't work. And suddenly we were faced with not being able to get back pictures and other science when we got to Jupiter. And the thing is about science out at in interplanetary space is you can't just go out and kick it loose. So we had to figure out how to make this spacecraft do what we wanted to do. And what resulted from a bunch of people coming together is we gave it a total brain wipe, gave it new brain over interplanetary distances, and it allowed us to condense the data down. And ultimately, we were able to bring back images like this one. This is a picture of the asteroid Ida, and this is the first picture that proved that asteroids can and do have moons. And this would not have been possible if we didn't have engineers from different areas of expertise that worked together and didn't give up in the face of failure, but instead we drew on our strengths and we worked together to come up with a solution. So fast forward to the present day. This is the talk about InSight, the Project InSight. Here's a mission that was designed to fly to Mars, land safely on the surface, deploy a bunch of instruments on the surface, and then just sit there and listen, quietly listen, taking the temperature, monitoring weather. There are so many things actually going on with this spacecraft at any one time. It sometimes boggles my mind. But before we go to being on the surface, we've got to get there. So let me talk a little bit about getting there. This spacecraft was originally supposed to launch in 2016, but there were leaks. Inside this instrument here, which is called the SICE, I'll talk a little bit more about that later. It's the main instrument that's on board or on the surface. It's listening for quakes. That's what we're trying to measure on Mars. So we don't call them earthquakes, we call them Marsquakes. And without this instrument, which wasn't working before we were set to launch, there was no reason to go. But instead of giving up, the project, which was built up of many different countries and people, groups of people, came together to figure out what we needed to do. This is just a sampling. Here's the InSight project. And these are the science agencies and companies and colleges that work together to make InSight work. And so engineers from France and the United States came together and redesigned the instrument using their strengths to make the instrument successful. And it was successful. And I'll talk about that in a little bit. So fast forward to 2018. Excuse me, May 5th, 2018 to be exact. The InSight spacecraft was launched from the west coast of the United States, and it took 205 days before it landed on November 28, 2019. But it didn't make this trip alone. This is a picture of two small spacecraft. They're called MARCO, MARCO A and MARCO B, the Mars CubeSat-1s. These are the first two interplanetary CubeSats. These are not very big. They're only, let me see if I've got the dimensions here. They're only 36 centimeters by 24 centimeters by 12 centimeters when they are folded up. And the success of these two satellites wasn't important to the full success of the mission, but they brought so much to the party. What you have to understand is Mars and space are not a nice place. And we've had a lot of different Mars missions that have crashed and burned or gone off into deep space, and we don't necessarily know why that happened. So a policy was put in place where we have to listen with another spacecraft in orbit when something comes and enters the atmosphere and lands on the surface. So anytime a rover lands or a lander lands on Mars, there are orbiters around Mars that are listening to it as it goes down into the atmosphere. But the problem is that while they can listen, they can't talk back to Earth at the same time, which means it could be as much as an hour or more between the time the spacecraft actually lands and when we know that it's safe back on Earth. Enter the Marco spacecraft. They were specifically designed to solve a problem, to listen and to talk back to the Earth at the same time, giving near instantaneous confirmation that the landing was successful. And I can remember sitting at JPL and hearing those signals, and believe me, it was exciting. Just one more example of spacecraft working together, or people working together to solve a problem, and this is going to benefit missions in the future. So we have a way to listen to the spacecraft on its way down to the surface and know that it survived or not. But that doesn't mean that the story ends there or even begins there. There's a process called entry, descent, and landing, or EDL. You can't just take a big spacecraft like InSight and throw it at Mars and hope it lands where you want it to. There is a ton of planning and design that goes in to make this process work. You have to consider things like how fast you're going when you enter the atmosphere. If you go too fast, you burn up. You have to worry about the angle that you enter the atmosphere. If it's too shallow, it's like a stone skipping off the water and you go away. Or you go in too deep and it burrows into the atmosphere and you're going too fast and you burn up. And you end up smacking into the surface. Smack. That's a bad thing. So, you know that if you smack into the surface, it's a bad day. So we have navigators that get us to the entry point as accurately as you can. Then you look down here. You've got to build your spacecraft and design it so that you've got a heat shield that will take care of the heat. I mean, it's going to burn, but you don't want it to be so thin that it burns right through and burns your spacecraft, which ends up, you got it, smack. Or it's too heavy and it ends up going too fast, doesn't slow down, and smack. You want to design it so that when the parachute that slows you down, it actually comes out and doesn't tear up as you're going in, or otherwise, yep, you got it, smack. So there are so many different things, so many different parts that have to work together that you need to have a crew of people, a team of people that have different experiences, different positive and strong ideas of how to work together and design their pieces, and then somebody else to pull all those pieces together. And what we needed is that group of people working together to make sure that we got there. If one piece failed in that 6 minutes of entry, you'd smack. We didn't smack. And just for fun, I thought I'd show you. This is a picture from orbit around Mars. And you can see from these pictures, here's the whole surface of the area. You have that heat shield that was ejected. We can see that. We can see where the lander itself landed. And the parachute and the back shell, those were off here. So this shows you that we were, in fact, successful. So now that we figured out how to get there, you kind of need to go back and figure out, why did we want to go there in the first place? Because We needed to select our landing site very, very carefully. This is where the science comes in. InSight went to Mars for very specific reasons. We don't know what it's like on Mars. We don't know if it's hot, if it's cool. I mean, we can measure on the surface, but what is it like inside the planet Mars itself? You can see some of the structure. Everybody knows that there's a crust, that there's a mantle between the crust and the actual core. But we don't know, what is that core? How does it behave? How thick is this mantle? How thick is the crust? So those are the types of questions that we want to get answers for. And you can see some of those questions. Is it active? Are there, in fact, quakes going on? We know that inside the Earth, there is a core, and there is heat coming out of that core. Well, is Mars the same way? Does it have a core? If so, how much heat is coming out of that core? So we're learning things about Mars and what it will do. And you may ask yourself, well, why should I care here on Earth about Mars? Because it helps us understand better how planets are formed and why they are not all the same. Look at our own solar system. We have planets that are covered with gases like Venus, or they're rocky like the Earth and Mars, or they're big gas giants. Why did they form in different ways? We can look at our moon and get some information. We can look at the Earth and get more information. But by going out to Mars, we get another set of information. And this allows us to keep asking questions and getting answers to those questions. Because quite frankly, the moment we stop asking questions and trying to get answers, that's when our civilization will die. And I don't think anybody wants that. So my entreaty to you, please keep asking questions. So we're getting answers to those questions by listening very carefully with some sensitive instruments. But to listen carefully, we have to be in a place where it's quiet. And we have to be in a place where it's flat. And we don't want to land where we're on a mountaintop or there are a lot of big rocks. We need it to be sandy because one of our instruments, the HP cubed, needs to be able to burrow down into the surface by about 3 or 5 meters. It needs to be relatively close to the equator so that as the planet goes around the sun, we get energy from the sun on our solar arrays and we stay alive. At nighttime, we have enough energy to stay warm. We have things that take energy to work, like a drill that needs to, or a hammer drill that keeps drilling down into the surface. So we found a place called Elysium Planitia, and I think I'm pronouncing that correctly. It's been a long time since I took my Latin. But here you can see, yep, we are here. We landed right there. We are very close to the Curiosity rover. You can see that there are not very many spacecraft that have landed, and even fewer that are active on the surface of Mars. It's not easy to get there. But where we are, this is our new home. Here's a picture taken of the area around us. This is a nice panoramic view, and it looks boring. Nothing exciting, very few rocks. It all looks very sandy, and this is exactly what we like. It's boring. Boring is good. So now let me talk to you about how we're going to answer, remember those questions? So we have a number of experiments on InSight that were specifically designed to gather the data to answer those questions. Here's the first of those. It's called SEIS, which stands for Seismic Experience for Interior Structure. This is an extremely sensitive seismometer. It has to be sensitive because we expect the quakes on Mars will be much smaller than what we experience here on the Earth. In fact, just this last weekend, we had a 4.6 magnitude earthquake that was 10 miles away from me. It woke me up. We don't expect those types of quakes to happen on Mars. Let's see. In fact, what we expect this instrument to be able to do is we expect it to be able to detect when a meteor impacts on the surface of Mars anywhere on the planet. It's that sensitive. In fact, it's so sensitive that just the wind blowing by can disrupt its measurements. And that's why we've got this shield that's sitting over the actual instrument. But even with that in the way, the instrument is so sensitive that it can measure changes in the surface due to a small dust devil going by. And in fact, we have measured dust devils going by. So in order to be as accurate as possible, the instrument takes into account things like temperature variations, wind that is blowing by, pressures that are changing, and even vibrations of various parts of the lander itself. So think about it this way. You're sitting in your house and you have a truck driving by on the road next to you, and the wind is blowing hard against your house, and there's a thunderstorm in the distance. How would you know that somebody dropped a stuffed animal or a book in a room on the other side of the house? How would you measure it? You would have to take that measurement and then subtract out everything else that was going on, like the truck and the thunderstorm. And then you would get the data for your observation. InSight has a whole series of instruments. We've got wind and temperature sensors on either side, so we can tell from one direction or the other. And we've got a pressure sensor that will tell us what is the weather like on Mars. And bonus, we have a weather station on Mars. And in fact, there is a place you can go to see what the weather on Mars is like at any one time. So another experiment that we're conducting on Mars is called RISE, which stands for Rotation and Interior Structure Experiment. Something you have to understand about NASA and JPL is we like what we call acronyms. We like to take long sets of words and compress them down. It's just the way we are. So I apologize if I drop too many of these acronyms and you don't understand what they are. Feel free to ask. What we do is we use two radio antennae on the lander, and then we measure the radio signals from those antennae to and from the Earth. Now, I'm sure you know about the Deep Space Network, especially the one at Canberra. I think this is a picture out at Goldstone in California, but you get the picture. Large antennas pointed at Mars, and they're measuring the radio signals that are getting to Mars and coming back from Mars. And we measure the changes in the frequency. So this is called Doppler shift. And I'm sure all of you have stood by the side of a road and you hear a motorcycle sailing up to you and then zipping away. What you're hearing is it's getting louder as it gets closer, and the frequency is getting tighter. It's getting higher pitch as it gets closer. And then as it goes past you, the pitch drops off and it gets softer in sound. From the signals that we are getting between Earth and Mars, scientists are able to take those measurements and they're able to figure out where InSight is on the surface of Mars and where, as it's rotating around, it's on the surface of Mars to within 10 centimeters. And that, to me, is real impressive. But why are they doing it? Well, what they see is that Mars doesn't actually spin exactly around its axis and it's not stable like you would expect a gyroscope or whatever. Now, here's where I'm really sorry that you can't see me. I'm doing an interpretive dance, as it were. I'm spinning around, but let me use this picture instead. As during a Martian day, it rotates, Mars rotates, it doesn't stay exactly around its axis. That axis actually moves a little bit. There's a little bit of a wobble. And over time, that wobbles. And this is called nutation. But what we're doing is we're measuring it over a long period of time, and then as time progresses, the axis of Mars will, and this is over thousands of years, would go to the other side and be pointed away. So the scientists are able to use the information from these measurements to figure out how is this planet wobbling. And from that, they're able to determine and infer what the core and what the mantle look like on this planet. And don't ask me to explain it. I just figure out how we get the observations. The scientists are the ones who can turn it into usable data. So, moving on. The next experiment that I want to talk about is the heat flow and physical properties package, or HP cubed. This is essentially a thermometer that InSight is using to determine how heat is moving from inside Mars toward the outside. The intention is to have this piece, called the mole, hammer its own way down into the surface of the planet about 3 to 5 meters. Now that's way deeper than anything a Mars rover or previous landers have been able to do. The mole has a mechanism inside it, and I'll show you a movie of how it works in just a moment. But it hammers its way down, down, down. And as it's doing that, it's trailing along a tether that has sensors every so often all the way along. And as it goes every half meter, it is intended to heat up here at the mole and then measure the temperature as it goes up toward the surface. And from that information, we're able to tell what type of material we have here. And the deeper we get, the better it is for us. Now, the mole nominally does the hammering on its own. Ignore the words on this. This is something that I dragged, but I want you to watch off to the left side how the mole hammers itself. Oops. No. Hang on. See, technical difficulties. All right. Watch as the mole hammers. You'll see it pulls it up and slams, pulls up and slams. And as it's doing that, it's digging deeper and deeper and deeper into the surface. So this mechanism that you see working pulls it up, a spring slams it forward. And there was another spring that was stopping some of the rebound. But that's not enough to stop all of the rebound. We also need the friction as the mole is going down, the friction of the soil against the side to help counteract some of that rebound. And like I said, while it's doing that, it gets down a certain point, it heats up, and then measures as the temperature dissipates towards the surface. So we have this really cool idea of measuring for earthquakes or Marsquakes, measuring the temperature. And if only we could get it all to work as it was intended, life would be great. But there's one thing I've learned over the years: it doesn't always go according to plan. You remember the antenna on Galileo? It didn't open up like it was supposed to. Or in this case, the mole isn't getting where we want it to go. During the early days, what happened on InSight is we used this arm to take this instrument off the deck and put it on the surface and get it all adjusted. Then we used the arm to take this support structure and put it on the surface. And that was all great. We got this size down, we got the shield put on, everything was going great. And then we went on to HP Cube, got it exactly where we wanted it to go, and we lifted the arm away and put it out of the way, and we said, mole, start hammering and do 3,600 strokes. And that took about 4 or 5 hours. And it appeared to make progress of about 30 centimeters down. And then we didn't see any more movement. So we said, okay, do another 5,000 strokes. and it did not make any progress. And instead, what we saw, I'm hoping this comes through for you, is that support structure. The mole was originally in this tube, and it was digging down, and it got down about 30 centimeters. This started to bounce around. That's not a good thing. And we had no indication of how far it had gone down beyond the 30 centimeters. We didn't know if it had gone further because our sensors didn't tell us anything more than that at that point. So here's where it gets really fun.
PJ, just a quick interruption. We have about 9 minutes left before we take questions.
Oh, man, I got so much to go.
That's what I'm telling you now. And
that's good.
Those people on the call, don't forget to type in your message or your questions so that way we have some form at the end.
Okay. So you can't go and look around and see what's going on. We have one camera that's on the arm. We have another camera that's on the side of the spacecraft. That's all we have to look with. We only have the arm with the scoop on it. But we figured out with all of these smart people at NASA JPL, we figured out how to pull that structure away. And this is what we saw. The mole was in the hole, yay, but look at the surface of the hole, the interior. It's not sand falling in on itself. It's actually what they call consolidated material. And that's a problem because now we don't have any friction. So we did a lot of testing. We figured out, all right, it's where we are. What can we do to help it along the way? It's not like we can stick this shovel on top of the mole and push down because we'll snap the tether. That would be a bad day. So what we did was we figured, but if we push that along the side and hit the mole here, oops, let me back up, hit the mole right here on the side and with the shovel, and then press down with the shovel, we give it a force, we give it a push down. And we did that. We moved up and we got it, and it started to move down. Yay, us. And then watch this. So this is the end of the movie. It'll recycle in just a moment. We got it here, right at the beginning. It's down near the surface, but we couldn't press as hard, and it backed out. And it did that not just once, and we got it moving again to go in the right direction. You watch, it will start to hammer in the right direction. It was making progress. Yay, us. But then it backed out again. So we were in a bad situation once again, but we didn't give up. We went back to the drawing board. Here is after it backed out the second time. And if you look real close here, there's this little tiny feature. Here's a picture. That little tiny feature. We decided we were going to try and place the scoop on that little tiny point and then push down on that little tiny point. Thing is, if you slip a little bit to the left, you rip the tether. You slip a little bit to the right, you fall off and you're no further along. And what amazes me about my team is they nailed it. They got us right where we needed to be, and we were able to push and get that mole going down. And here is the latest pictures of where the mole is. It is below the surface. We haven't snagged or torn any of the tether. We've gone about as far as we can go with the scoop. So now what we're doing is we're taking that shovel and that arm, and we are using it in ways it was never designed to do. We are scraping material. This is as far as we can reach. Scraping material into the hole. This is what it looked like before we did that first scrape. Here's after that first scrape. And we're going to scrape more material and press it down with the surface. So here's something else that you have to think about when you're operating a spacecraft on Mars, sitting in on your couch. And that's what we've been doing. We are operating this spacecraft from our couches. But you can't just joystick it. You have to be as accurate as you can and make fine determinations, because if you don't, like I said, it's a bad day. So we're scraping material into that hole, and now we've got the scoop that was inclined. It's pressed as far as it can go, and during the next week or two, we are going to pull back, take more images, and probably go back to doing more of these scrapes. So the fun doesn't stop there about Mars, though. I wanted to show you something that's really quite interesting. You may have heard a year or so ago, dust storms on Mars. This is what our spacecraft looked like after only being on the surface for 100 days. This is 475 days later. These are our solar arrays. They're supposed to be generating power. If you can't see the solar arrays, you've lost a lot of your power that's allowing you to fly your spacecraft, or in this case, operate your spacecraft on the ground. So we have to worry about how much energy we use. And we have to change the way we operate our spacecraft based on how much dust is in the air, because the dust in the air blocks the sun from getting to you, and then it drops out and lands on your spacecraft, and it accumulates. And before you ask me, I always get this question, why didn't you just take a broom or a blower and blow the dust off? Well, remember I talked about the fact that if your heat shield was too thick and heavy, you'd go plummeting in and you'd burn up. Any weight you take to Mars is oh so precious. And having dust, a broom or a blower, that takes mass, it takes energy, and we just couldn't afford it to get onto the surface. So I think that about does it. I did want to have you, give you a couple of points I'd really like you to take away. So before we get to your questions, wanted to leave you with 3 points. The first is look for opportunities to learn. Today is a good example of learning something you may never have heard about. Look for ways to understand other people. If you get to travel, great. Read about other places, great. You will learn different ways to think about what's going on and how to solve problems. Work as a team, not as a star. As I tell new people that join my project, this is not all about you. We are a team, we are a project, and if we work as a team, we will be successful. Somebody who wants to be in the limelight is not going to be as successful in a team environment, and you need a team to be able to do things like this. And finally, don't ever give up. Things don't work the first time, all the time. Don't give up. Try again. Come up with a new way to do things. You never know what that's going to turn into. This job that I have, like I said, is one of the coolest things I know. My wife likes to walk in and see me on teleconferences with other people and say, what are you doing? Oh, we're talking to Mars. We're getting pictures back. We're seeing what's going on. She just looks at me. You're talking to Mars? And when she says that, I realize I can never lose the marvel, the wonder about what I'm doing and where I'm doing it. I'm measuring for earthquakes or Marsquakes on Mars. And that has to be one of the coolest things I could ever do. How'd I do, Michael?
You did awesome. And we've got a few minutes left for some questions, should anybody want to type one in. So, PJ, I got to ask you, though, how important is creative thinking to you guys? I mean, science seems so straightforward, isn't it? Little math, little equations, whatever, and it's all straightforward.
Right. You would think that. And that is what you use to solve the problem. But the creative thinking is how you come up with the initial ideas. Who would have thought to send 2 spacecraft along with Mars, or along with Insight, to then play the role of listen and talk as we were going in. That somebody had to be creative enough to think, how can I do this on the cheap? Money is important. How can I do it on the cheap and with very little weight? How can I get this information back? And they came up with the idea. The mole itself, how do you get something to dig all the way down without it being a drill that takes a lot of energy and is massive? How do you do it? Well, you build in this hammer inside, and then you get to solve the problem with the math and the science.
All right, so we got some other questions that came in, besides my stellar ones, because I'm brilliant.
Of course you are.
Oh, of course. How much energy would the solar panels produce per sol?
I have another chart somewhere else. We were generating on the order of together, the two, we're generating on the order of 2,000 watt hours per sol. So we generate enough energy that over a 24-hour period, and we're not collecting obviously at night, but the total energy generated, the number we use is 2,000 watt hours per sol. That's what we had, that and more, right after we landed. Right now, the latest information that I saw is we are only generating about 1,000 watt hours per sol. So we've lost half of the energy that we had at the beginning. And that means we can't do everything we want all the time. We have to plan it together and put it together very, very carefully. Turning things off, making sure we don't get too cold at night. So you have to have heaters on at night, which means that you have to turn something else off during the day to give your batteries enough power to get you through the night.
All right. And so obviously you have batteries in there as well to keep it hot and all that fun stuff, or keep it warm. I shouldn't say hot. Here's a question that I always appreciate. Can an average person gain a job in this industry?
Well, what do you mean by average? I don't think anybody is average. I think you should look at my background. I was the third son of a high school teacher. He didn't make very much money. My mom stayed at home. She took care of us as a homemaker. And I was able, because I chose to, and my parents were supportive, I was able to go to college and get degrees, 2 of them, and find jobs at a place like JPL. Now, if I were sitting at home and chose to instead play video games all the time and not get a degree, then I should never expect to be able to get a job at JPL as an engineer. It's choices that you make and decisions that you make that will help guide and enable you to go be just about anything you want to be. I will never be a basketball player in professional sports. I'm not tall enough. So there are limitations. But my brain allowed me to come work here. So yes, to answer your question, it is possible for any average person to get to a job here at JPL if you choose the path that you need.
And I will also add that we don't just have engineers and scientists at JPL.
Exactly. No. Some of the most critical people that we have other jobs that may not require the same types of engineering and science degrees. Some of them do not require degrees. It takes a team. And Michael, you're an example. You have an education. You're in public outreach. You're doing that. You're working facilities to make sure that we have all of the pieces that we need to be successful.
My job is to support the rest of the team.
That's right. And if you didn't, we would fail.
Right. JPL is a small city. I don't know how else to put it. Between contractors and JPL direct employees, there's over 12,000 people at JPL. Obviously not right now. We have janitors, we have cooks, we have people who work on the elevators. We have the facilities people who keep the things running. We have accountants and lawyers and IT engineers, software developers, and then the vast majority of the people, we have our scientists, we have our engineers, and we have that other level of people. But it takes a city to keep things going at JPL.
It does. And it's like working on a school campus. You can wander around and you can see all sorts of different people every day when you're on the lab. It's really a fun place to work. But we're not trying to sell you on JPL.
No, but as Jackie brought up earlier, there are a lot of opportunities that you guys are having to work with other space agencies, not just JPL. The Japanese Space Agency, the India Space Agency. Australia is developing their own space agency.
That's awesome.
So if this is a field that is fascinating to you, you don't have to be a scientist or an engineer to support it. All right. I think we beat up that topic enough. How much energy does Insight use per soul? So you're saying you're down to 1,000.
Right. And that's over the course of an entire day.
Mm-hmm.
24 hours, 39 minutes, 35 seconds.
Now you got your batteries. Are you using it all?
So as we are in the real sunny part of the day, we are not using as much as we're generating, and it goes into the battery. And then at night, we draw from that battery because we're not generating. The plan that I'm working on right now, we like to have what's called margin. That is not a bad word, having a little bit of cushion. So we are generating on the order of 1,000 watt hours. We are using only 900 watt hours. So some of that excess energy goes into keeping things warm. Things are not exact, but we use on the order of 900 watt hours per sol right now.
All right, we're just about out of time, so I'm going to follow up with one last question. There were others. Again, excellent questions, everybody. Thank you for your interaction. What is the expected lifespan of the InSight mission, and what happens to it at the end of the working life?
So InSight is coming up on the end of what is called its prime mission. We landed, and it was expected to be on the surface and active for a minimum of 1 Martian year, which is, I think, 668 sols. So 668 Martian days. That's going to happen on October 12th. So we are really close to the end of our prime mission. We still have lots of life left in us. We are working with NASA headquarters right now to get extended for another 2 years. Let us go for another Martian year and continue to gather data. Measure. We have detected quakes on Mars. We can measure all sorts of things. The mole isn't where we want it to be. We're real close. We keep trying. But if we can get it down there, it'll be so much more advantageous. We would like to go for at least another 2 years, 2 Earth years. It's possible that if we are able to have energy and nothing breaks, we could go on for another 2-3 years beyond that. Some of the Mars rovers went on. They were supposed to last for 90 days or thereabouts, and they lasted for 10 years or more. It just depends on if you get lucky and a dust devil comes by and sweeps off some of the dust that's on your solar panel. You've got more energy. What happens at the end? We say, thank you for playing. We shut things down and we say goodbye. And then we fill out a bunch of paperwork, we write a bunch of reports, and we move on to our next project. And that's how the game is played.
Well, that concludes our time, unfortunately. We had quite a few other questions that we could have looked at. Yes, we do have some Australians that work at JPL NASA, so there's a quick one for you.
Like I said, don't stop asking questions. And just because your question wasn't answered today doesn't mean it won't get answered. I will get you an answer through Bobby or through Jackie, and then keep asking those questions.
Thank you, everybody, for your time. Enjoy your next classes. Have a wonderful day.
Thank you.